All right, good morning. So today we're going to continue talking about the continuity relationship and look at some examples that help to illustrate its importance and application. Before we get into those, let's just take a look at a couple of announcements. And I wanted to point out one thing, and that is that you've got back-to-back homework assignments for next week. And the reason for that is I used to just assign a single assignment for Chapter 5. It was kind of lengthy, and so I decided instead to break it up into two segments and have a couple of days in between. These problems are not particularly complicated. In fact, a lot of them are just Q equals VA, similar to what we've been working with so far. So I think you shouldn't necessarily be intimidated by the length of the number of problems there. But I would encourage you to get an early start all the same, since you've got one due on Tuesday and one due on Thursday of next week. Any questions before we get into the new stuff? All right. So we saw this figure before, and what we were talking about is keeping track of fluid particles of interest and where their location changes over time. And we had the idea that there are control surfaces through which we monitor the flow of fluids. And on the inside of the control surfaces is a control volume. What the Reynolds transport theorem says is we can draw that boundary of control surfaces and control volumes and keep track of storage and transport. So storage is the area inside of the control volume, and here what we're saying in this first expression is that we're going to find out the change over time of the mass inside of that storage area. And so here we have the density multiplied by some changing volume over time. And in class last time we learned about mass flow rate, the variable m dot, where it has units of kilograms per second. And so if we have volume, which is cubic meters, and density of a fluid, which is kilograms per cubic meter, and then we throw in the change of time, which would be units of seconds, and you can see that the resulting units of this first storage term is going to be kilograms per second. And so in the Reynolds transport theorem, we're saying let's consider the accumulation of fluid mass inside of the CV, inside of the control volume. And then also consider the flow of mass through the control surfaces. Now I want to point out here that there's two different V's. The V with the cross through it, the strikeout, that's volume. This other V is velocity. And so this second term, the transport term in the Reynolds transport theorem, let's look at that one. So we've got velocity times area, so that's volumetric flow rate. Remember, we've been saying so far Q equals VA. So we've got V times some differential area, that's just the zone that the mass is flowing through, and multiplying it by the density. So again, we have units of kilograms per second for the transport term. It's just saying that we've got some area. In the case of this illustration that we looked at last time, we had an inflow and an outflow. We'll have some examples and homework problems where you'll have multiple streams that you're having to keep track of, but the net difference is going to affect the change of mass inside of the control volume. Now on the left-hand side of the equation, this is saying that the mass of the system can change over time. And the Reynolds transport theorem begins pretty generally because there are situations where there is a reaction, for instance, inside of a reactor, and so the mass of a certain constituent may be increasing or decreasing over time, depending on the nature of the reaction. But if we've just got fluids that are conserved and there's no reaction, then we're going to have a situation where we say, let's have this left-hand term cancel out to zero. So here we're just defining all the terms that we've already talked about. So here it is again, the Reynolds transport theorem, but let's say that there's no mass being created or destroyed. So if we set the changing mass of the system over time equal to 0, and we just say that there's flow in of the system and accumulation and flow out, then here's how the Reynolds transport theorem, we're going to apply it for the rest of the course in fluid mechanics, looks like. There's just the accumulation of mass in the control volume, and that's completely accounted for by the net mass efflux. And so net is meaning the difference between the in and the out. And so the simplest expression for the Reynolds transport theorem might be that the mass inside of the control volume over time is the difference between the mass flow rate in and the mass flow rate out. So in other words, if we have some black box, it's just a location where fluid can accumulate, and we look at the mass flow rate in and the mass flow rate out, if there's more in than out, we'll have a positive accumulation. And if there's more mass flow rate out than in, like there was in that Oahe Dam example that we worked at the end of class last time, we're trying to find out how long it would take to drain that reservoir. In that case, there was a negative accumulation, and so the mass inside of the control volume over time was decreasing. Any questions so far about the Reynolds transport theorem? I mean, it's easy stuff. You can reduce it down to accumulation equals in minus out. Now, like I said before, Chapter 5 is a really simple idea, continuity, but we're going to be applying the principles of Chapter 5 to some of the concepts that we've had in other sections of the course so far. And you remember that when we were discussing flow visualization, we talked about the difference between Lagrangian environments and Eulerian approach to calculating fluid pressure, for instance. And so in the Lagrangian approach, what the idea there is tracking individual particles and their trajectories over time. So if we wanted to find out how a nozzle of changing diameter affected the fluid pressure, what we could do is apply the Lagrangian approach and try and keep track of individual particles that are following a certain streamline, and looking at, by integrating Euler's equation from one location to the other, or maybe applying Bernoulli's equation if we had steady flow, then we could find the pressure change. But the challenge with the Lagrangian approach is just that there are so many fluid particles in any given system. And so a simpler method for finding out how pressure might change through a flow field like this is to divide the flow field up into elements. Now, we've just been talking about the Reynolds transport theorem, and the idea there is that there are some control surfaces that fluids flow through, and inside of the control surfaces are control volumes. And so when we develop a mesh through a network, and that's what's being illustrated here, you can think of each one of these flow elements as a control volume. And so something's going to be flowing into the control volume, flowing out, and fluids take their properties with them through those flow fields. And so the Eulerian approach says that if we want to know the flow properties at a single point, what we can do is apply the free body approach to all of the elements in this system. And there's a lot of elements depending on how fine the mesh is, but many fewer elements than there would be if we're tracking individual particles. And the other thing that simplifies this computationally is that the trajectory of the individual particles in the Lagrangian approach was unpredictable. You know, they're moving in a random direction sometimes, and there can be these vortices and eddies that complicate the flow patterns, whereas the Eulerian approach allows us to say, here is our control volume, the control surfaces are fixed, and so it takes some of the uncertainty out of doing the calculations. We can, in other words, apply the types of equations that are limited to Lagrangian ideas. Remember, the Bernoulli's equation has the four limitations, that it's for an incompressible fluid, that is inviscid, for steady flow, and along a streamline. So strictly speaking, we should be forced to apply Bernoulli's equation to situations where we're working along some streamline. But because of the complications of that, with there being so many particles, the Reynolds transport theorem is sort of a way to bridge the gap between the Eulerian approach of working in a mesh environment, but also wanting to use some of these other equations. Okay, so with that background, we're going to, through the course of Chapter 5, look at some cases where we kind of combine the two ideas together of control volume and then also like changes of pressure and changes of location. But just to take another look at the idea of reservoirs and volumes changing over time, I'd like you to consider this case. So we have a tank of water where we know the diameter. It says here it's a circular tank with a diameter of 0.5 meters. So what that's talking about is not the diameter of the opening and not the diameter of this jet of water that's coming in, but it's the diameter of the circular tank. And so we're going to want to know the cross-sectional area of the tank. There's a flow in and a flow out. Now, the outflow here is not an open orifice. We can tell because that's a thick black line there. It's an outflow pipe where somewhere downstream of what we're seeing, the flow rate is being controlled, probably with a valve of some sort, because the flow rate is fixed and unchanging. If it was an orifice, remember from the lab that we had this week, the flow rate out depends on the height of the water. And if the height of the water is changing, then so would the outflow rate. But here, we're just simplifying that and saying we've got an outflow of 0.003 cubic meters per second. And for the flow that's coming in, we know its velocity and the cross-sectional area at a certain point. So what I'd like you to calculate is what's happening to the liquid level. Is it getting deeper? Is it getting shallower? Or is it steady? I guess that's the third option. But if the liquid level is changing, find the speed at which it goes up or goes down. Okay, so there's more coming in than there's going out, right? The difference between the two, there's 17.5 kilograms per second coming in and only 3 kilograms going out each second. So that means that the net accumulation is 14.5 kilograms per second. So we know that the liquid level is going to be rising, but the question ultimately asks, what's the speed that it's rising? So the velocity, or if it's rising, then it's going to be, that's the direction component of the velocity. So the first thing we can do is convert that from a mass flow rate to a volumetric flow rate. Remember, the relationship there is m dot is density times q. Or q is going to be the m dot, the mass flow rate, divided by the fluid density. So 0.0145 cubic meters per second of water is accumulating. Now the critical thing here is the cross-sectional area of the tank. And so think of it this way. If this tank has a really big diameter, then the liquid level is going to be accumulating slowly. But if it's a relatively narrow tank, like maybe the graduated cylinder in the lab, the liquid level accumulates quickly there because the cross-sectional area is low. So in this case, you can calculate the cross-sectional area with the given diameter. This 0.5 is the diameter. So the area for that diameter, I think I calculated it up here, pi d squared divided by 4. So the cross-sectional area is 0.196 square meters. So then the rise velocity, we'll just have the Q accumulation divided by the area of the tank. And there are several problems on the homework where you have to apply that same idea of the area of the tank, and then that affects how quickly the fluid level is increasing or decreasing. So 0.0738 meters per second. Who got that? All right, great. Very good. Any questions about this example before we move on? Yes?
So if the tank was like a cone,
Ah.
how would you apply the equation to that?
So if it was a cone, then we could calculate the velocity that it's rising at a given instant. You know, like if we knew the cross-sectional area at this moment of time. But we'd need an equation that would be relating, you know, like if we wanted to find out over time what's happening, we'd need an equation that relates the diameter to a certain depth to be able to describe that more than just a given instant. I think there's it's not a cone, but there is a problem in the book, although I don't think it's on your assignment, where they have a tank with two different diameters. There's like the lower diameter and then the upper diameter, so you have to divide it up into two periods. The period with where the water level is going to be rising quickly, and then the other period when you've got the larger diameter where it's decreasing. All right, so consider this. We have a control volume. It's a tank. And at B, the piston is moving to the left at the rate of V. And at A, and so what that's doing is that's pushing water into the control volume. All right, at A, the piston is also moving to the left, but it's moving to the left at 2V. And so that's drawing water out of the reservoir. So the question is, what's happening to the water level here? Remember, the three options are you can have an increase of mass, and so there's positive accumulation in the tank, which would mean the liquid level is going up. There can be a negative accumulation in the tank, which means the liquid level is going down, or in equals out, and the liquid level would stay the same. So what's happening here? What's happening to the water level? Okay, so raise your hand if you think that the water level is going down. Down would mean that there's more out than in. What about if the water level is going up? A few hands. What about if it's staying the same? I love tricking you guys. I love tricking you guys. All right, so why is it not staying the same? Why is the water level not staying the same? Diameter squared. Ah, yeah. So remember, I set this up specifically to make it look appealing, right? To make it seem like, oh, in equals out, right? So the trick is that here you have the diameter at B is 6, but the diameter at A is 3. So it seems like, oh, well, that has double the diameter, but this has double the speed. Remember, what's volumetric flow rate? Volumetric flow rate isn't diameter times velocity, it's area times velocity. And so area is pi d squared divided by 4. And so here at B, since the diameter is double, then the area is 4 times as large. So in this case, there's going to be more water coming in than going out. Just as a proof of that, let me show you. Okay, so we could calculate the area of both of those cylinders that's either pushing water in or drawing it out. The area at B, although it has double the diameter, has 4 times as much area at B. So if we think about the flow rate in, you know, we can solve this in symbolic terms. Since we don't have an absolute velocity for V, we could just solve it in terms of V. So the Q in would be 28 times V, And then the Q out is just going to be 14 times V. So it would be whatever the area is multiplied by the velocity. In this case, the velocity was 2V. So there's more going in than going out. That means that there's going to be, if we think about it in terms of the mass flow rate, then we'd have to multiply the density of whatever this fluid is by these two expressions for the Q in and the Q out. But it's going to be a positive value, regardless of whether the fluid is oil, mercury, water, whatever it is. We could calculate the net accumulation. So does that make sense? No one's going to fall prey to that trick. I mean, I won't put it on exam now that I told you about it. I'll try and think up some new trick, but. All right. Any questions? No, in reality, just because I'm not trying to trick anybody on exams. I'd rather know that you understand the fluid mechanics than catch you on a technicality. All right, so let's look at this problem, because you have a homework question that's very closely related to this one, and so I think this is important. This example is important to understand. So we've got a circular pipe and a solid cylinder that's falling downward through that pipe. Now sometimes in problems like this, the hard thing is to think of where are the control surfaces, what's the control volume. You know, like applying the idea of the Reynolds transport theorem to a situation like this may be the tricky thing. And so, does one of you have a marker? Is somebody better prepared than I am? Perfect. Thank you very much. All right. So, we've got a hollow pipe that's full of water and a cylinder that's falling down through the center. And we've got the dimensions that are given there. Now, as the water goes down, as the cylinder falls downward, it's pushing water around the outside edge. And so think about what this looks like in a cross-sectional view. We've got the outer pipe and then a solid cylinder. And so it's kind of like a donut shape. And the water is flowing through that donut shape. And so the question is, take a moment and try and figure out what would be good control surface boundaries to draw in a problem like this. Because what we want to do is figure out where is the water going in, where is the water going out, and is there any accumulation. You know, that's how we apply the Reynolds transport theorem, is by selecting control surfaces and then keeping track of this accounting process of in versus out. So let me pause for a moment and give you a chance to try and sketch some control surfaces for a situation like this. All right, so here on the whiteboard I've drawn a sketch of what we could have for our control volume. And the idea here is that something is going to be entering the control volume and something is going to be exiting the control volume, but there's no capacity for storage inside of that pipe. You know, the control volume is already full of a liquid that's incompressible. And so if something enters that control volume, something else is going to have to go out, because there can't be an accumulation of mass inside of that space. And so what's happening is the cylinder goes downward, the water in front of the cylinder, and then eventually the cylinder itself is going to go into that control volume. And so if the cylinder moves down and displaces 1 liter of water, then that 1 liter of water is going to have to flow around the outside edge of the cylinder. So here, in equals out for this application of the Reynolds transport theorem. There's no accumulation inside of here. So then the question is, we want to know the velocity of the water around the outside edge. So we know that the velocity of the cylinder that's falling down, and you can calculate, therefore, the flow rate of water that's being displaced by that cylinder. So think about, what if this control volume is fixed in space, and we've got the cylinder passing through the control surface of the control volume. And so if the cylinder is moving at 1 meter per second, the question is, what will be the velocity of the water around the outside edge? So I'm going to give you a few more minutes to continue thinking about that, discussing with your classmates, and we'll find out what's the velocity out. Okay, 1.29 meters per second is the answer. So, so we've got this cylinder falling downward through a tube. And as it falls down, it's going to be entering our control volume, and it's going to be pushing water out of the control volume. And so what we need to know is, what's the flow rate that this cylinder is entering the control volume? And remember, it's the idea of flow rate isn't limited necessarily to liquids. The units of flow rate is simply cubic meters per second. And so this cylinder that's falling down, there is a rate, a volumetric rate, at which it's entering this control volume. And if we know the volumetric rate that it's entering the control volume, then that's the same rate that the liquid is being forced out around the outside edges. And so you can see here on the board, I found the flow rate in terms of the area of the cylinder and the given 1 meter per second velocity of the cylinder. So it's 0.01767 cubic meters per second. And there's no accumulation. There's no place for the water to be stored. And so the flow in is equal to the flow out. So I start the flow out term by knowing the Q out is that same 0.01767 cubic meters per second. And so if I want to know the velocity out, it would be the Q divided by A is what gives me the velocity. Now the trick here is using the right area. And it's not going to be the overall area of the tube, because the water can't flow upward through this falling cylinder. The water has to go around the outside edge, and so I referred to it on the other whiteboard as the net area. So the net area is where the water is going to be flowing through, and so it's the difference between the tube and the cylinder. The tube is the big diameter, so we find that area based on the diameter of, I think it was 200 millimeters, yeah, 200 millimeters, minus the area that's based on 150 millimeters. So in the end, you should have a velocity of out of 1.29 meters per second.
So if this were a pipe falling through a pipe, inside of that one as well as distance around it.
If it was a pipe falling through a pipe?
Yeah.
Okay.
So a hollow cylinder.
Okay. Then you'd need to know how thick is the pipe, I guess.
So you'd have to calculate
Yeah.
water what's through the middle.
Through the middle, yeah, right. Okay, any questions about this example? All right. This week in lab we talked about the orifice equation, an opening in the tank where how high above the orifice we are dictates the outflow rate. And so the orifice equation, if we say that there is a perfect conversion between the potential energy and the velocity that comes out, then it's the square root of 2gh. Now, of course, in the lab I told you about the coefficient of discharge that accounts for turbulence and energy loss as the water exits the orifice. But the the problem like this is we can keep track of where the water is over time, and here we have, in this figure that's shown, no flow rate in, just a control volume where the mass is decreasing over time inside of the control volume. So if we were going to apply the idea of the Reynolds transport theorem to this situation, we'd have flow rate out, but no flow rate in. Some practical locations where we would apply the Reynolds transport theorem. This is a diagram of a wastewater treatment plant. And eventually some of you are going to end up taking the environmental engineering course. Some of you won't take that. I pity you. It's a great class. You're going to be really missing out learning all about wastewater. But in a lot of facilities, because people use water at varying rates during the day. You think about in the morning when people are showering, and in the evening when people are washing dishes and maybe washing clothes. There's a huge variation in water consumption during the day, and so there's also a variation over the course of time in how much water is making its way through the collection network and going to a wastewater treatment plant. And it's bacteria that are living inside of the treatment plant that actually break down some of the pollution. And you can't have a huge surge of water during certain times and expect those bacteria to be able to react really nimbly to that. And so because of this problem of big variations in the daily flow of water that's going to a treatment plant, what we really want is to dampen down those variations. And we'd rather have it so that the bacteria are receiving a constant load, not only in the volume that's flowing through the treatment plant, but also more variation in the strength of the wastewater. So flow equalization basins are used in a lot of cases to dampen that temporal distribution. Temporal distribution just means the characterization of when things happen over time. You can see this temporal distribution is saying that wastewater comes to the treatment plant at lower flow rates at night than those flow rates are coming to the plant during the day. And so if you have a big tank, then over the course of the day what you can have is periods where you're capturing additional flow that's higher than you want to be going through the treatment plant, and then releasing it during the evening when the flow rates coming into the plant are relatively low. And so you'll notice here from, it looks like midnight to about, maybe 8 o'clock, the flow rate is less than the average daily flow. So if you had a big storage reservoir, what you could do is you could take the area above this line when the flow rate into the treatment plant is more than the average daily flow, capture all of that, and then you'd release that excess flow at night when the treatment plant isn't receiving naturally as much water as the average. And so I think I have a picture here. This is in the notes, right? I took some students to a wastewater treatment plant. You can tell they're really excited. This is like the enthusiasm you're giving up on. If you're a mechanical engineer, you're not going to take wastewater treatment plant. You're giving up the opportunity to visit a wastewater treatment plant. But here's one of those flow equalization basins. And it's essentially just a big wastewater storage tank, and they have to add oxygen to it as well because the waste is being broken down by the bacteria that are naturally occurring in the waste. And so if it was to deplete all of the oxygen, then it would add quite a bit of a bad odor to the area that it's in. And that particular wastewater treatment plant is pretty close to a really expensive neighborhood in Dubai. So people don't pay millions of dollars for a house only to have like the smell of a wastewater treatment plant. So you have to be a little bit careful about some of these storage basins, but the main idea here is that we can use the idea of accumulation in combination with a treatment process that's microbial, because the bacteria don't respond as quickly as a chemical reaction or a physical reaction would. Okay, so before we finish up for today, I wanted to take a look at one of these homework problems that you've got on your schedule for next time. Now, in this problem, we have multiple streams. We've got a flow coming in, a flow going out, and we're given the cross-sectional area of the tank. Now, they are defining the rate of accumulation by telling you that the water level is rising at 0.1 centimeter per second. So, you know, the governing principle in this problem is just that the difference between in and out is the accumulation. And it's just at a given instant of time, though, that you want to find the velocity out, because the velocity out through this orifice, where we would apply the square root of 2gh, that's changing over time. But right now is where h is 1. So you can find the outflow by multiplying the velocity out through the orifice, and then they're giving you the cross-sectional area at the orifice. So once you have the V out based on the orifice equation, you can find Q out. And then the fact that the water level is rising tells you that there's a positive accumulation. And so there's going to be a positive accumulation. We've got some flow rate out. The question is, how much has to be coming in to make all the rest of that true? So you'll calculate the Q in, which is simply the difference between the accumulation and the out, and then turn that into a velocity in by Q equals VA. So this is a combination of the orifice equation, which comes from Bernoulli's equation, and the accumulation inside of the tank. If you have questions on the other homework assignment problems, I'd encourage you to stop by during my office hours. So let's just take one last look at these announcements before we finish for today. One assignment is due on Tuesday, the other is due on Thursday, and I know that seems like a lot of problems, but I mean, it could be worse. In the past, I had that entire block due all at once. I've tried to spread it out a little bit. It's like a homework flow equalization basin, I guess, trying to distribute the load. Anyways, all right, have a good day. I'll see you on Tuesday.